So another important part of vector algebra is cross product. The geometric definition involves taking the two vectors, in this case A and B, finding the angle between them, that's theta, drawing a perpendicular to the plane formed by A and B. If you take this and just imagine that it forms a plane, draw the perpendicular to this plane from A and B, and that'll give you the direction of the cross product. The magnitude of the cross product goes as sine of theta. If you have theta going to very small angles, sine of theta goes towards 0, then the vector product will shrink, and if you open this up, it'll increase. The vector product is not commutative. In fact, it's such that if you switch the order, you get a minus sign. The cross product is distributive. You have A cross times a sum, B plus C. Then you can distribute that so that it's A cross B plus A cross C. So notice that if you have A parallel, which is what I was implying before, that as you go towards 0 degrees, sine of theta goes to 0, and the cross product goes to 0. A cross B is a maximum at theta equals 90 degrees, where of course the sine of theta goes to 1. Here's an important application, or actually helps us see what the cross product looks like, and that is to show that the magnitude of the cross product of A and B, so this quantity right here, is equal to the area parallelogram with sides formed by the vectors A and B. So the area of the parallelogram with sides for the two vectors, we want to show that that's equal to the cross product. So here's our two vectors, and the parallelogram we're talking about is to draw the parallel to this side over here and the parallel to A over here, and so that forms this parallelogram. As you can see, in terms of area, if you were to take a projection of A onto B, so it's this line right here, this distance here is the projection, we form a triangle with the same angle theta here. So if we take this triangle here and just bring it over here, what we form is a rectangle. So it's this rectangle right here. Well, we know how to calculate the area of a rectangle. It's just the two sides multiplied. This side here is equal to the length of B. And this side here is related to the A and the angle, namely it's equal to A times sine of theta. So here's our B on this side here. So this side over here has the same length, B. This side of the rectangle is A sine theta. If we do this trick of moving the triangle over here, then we have that the height of the rectangle is equal to this, and the length of the rectangle is this. So the area of the parallelogram is exactly equal to the magnitude of the cross product. If you had these two vectors here, you wanted to relate it to this concept of a parallelogram, you can see that if you make the angle small, the area will get smaller and smaller, go to 0. If you widen this, the maximum area of that parallelogram will be when you have a right angle here. This means that the magnitude of the cross product is largest when these two vectors are perpendicular. If A and B are parallel or anti-parallel, so for example, if we have B and A is supposed to go along here, and here we have B and A in the opposite direction, if either of the vectors is the 0 vector, we'll get 0. In these cases here, where we have sine of theta equals 0, here we have sine of theta equals 0, so you have theta equal pi, theta equals 0. Then you'll get 0 for all these cases, and of course if you have a 0 length vector, then that's going to give you 0. Theta equals 0 or pi, sine of theta equals 0, or if one of these or both are 0, then you get 0. For either case, the cross product equals 0. And that's what we call the 0 vector, because the cross product is a vector. So for either case, the area of the parallelogram goes to 0 and the magnitude goes to 0. If you have a triangle formed by these two vectors, then what's the area of the triangle? So this should be area. we've already shown that the cross product magnitude is the area of the parallelogram. And although I've drawn this poorly, this area equals this area. So the area of the triangle is just 1/2 times the magnitude of the cross product. So the area of the triangle is just what we said, 1/2 times the A cross B magnitude. So the question next is the cross product commutative? The answer will be no, because if you take B cross A and change the order to A cross B, you'll get a minus sign. The way we work this out is that if you take the two vectors, let's say A and B like this, in order to find the direction of the cross product, you can use the right-hand rule and you twist A into B like that. Your thumb will then point in the direction of A cross B. And in this case here, A cross B would go down like that. That's the geometric rule for finding the direction of the cross product. So if you switch the direction, your fingers will point in the opposite direction, and so the cross product will switch directions. This is called the right-hand rule for obtaining the direction of the cross product. So if you have A cross B equaling this quantity here, we ask, is this statement correct? The answer is no, because this quantity here is a vector, whereas this quantity here is a scalar. So the correct expression for A cross B is the magnitude of the cross product times a unit vector, which is the unit vector normal to the plane formed by A cross B. One more time, this statement is incorrect because this is a scalar, this is a product. And we fix it by determining the normal vector that's suitable for the direction of A cross B. So if we now take vectors to make up the unit vector pattern that we have here, remember that I and j are along the x and y axis, and to find the z direction we use the right-hand rule, where we put our fingers in the direction that x rotates into y, and our thumb points in the z direction. So if we take the unit vectors where we just take the self-cross products, we have two parallel vectors, and so we end up with 0. So I cross I, j cross j, k cross k are all equal to 0. The non-self cross products, meaning that we take different directions, give us two perpendicular vectors, so that sine of theta is equal to 1, and so the length is equal to 1. Now be careful, because you could take the order such that you get a cross product is in opposite direction of the third vector. In general then, if you have different unit vectors, which we'll represent by E1 or E2, E3, that if you take the cross product of E1 and E2, you do get the other unit vector, but it could be plus or minus. So just take the example of I cross j, take your fingers, do the same thing that you did with the axes, and you get the unit vector k. If you take the opposite, if you take j crossed into I, then that'll switch the direction and give you a minus k. So if you play around with all the combinations, I encourage you to do that so you can see how they become plus, minus, and so on. The important thing to notice is that because you're in a coordinate plane here, the unit vector, which has to be normal to that plane, will always be along the other coordinate axis. So here's the picture here, and I've started a table of finding these cross products. And so I've got, for example, j cross I, which we talked about, it's minus k. And I've got k cross I, which you can determine is equal to j. And so now I'd like you to fill in this table, so you've really just got 2 values here and 3 here. So take a couple minutes to do that. Time's up, so let's see what we get. Let's take this one here, I cross k. So if you come up here and take I cross k, use the right-hand rule, and you'll get a vector pointing in this direction. Because these are unit vectors, its length is 1, so therefore it's minus j. And you can compare your results with these factors here. Let's expand A cross B in Cartesian coordinates. So we'll consider the two vectors, for example, A and B, like this. And we're going to use the fact that the cross product distributes. We're going to take the A cross B plus C and set it equal to the sum of the two cross products. Okay, so this is like what we did with the dot product. We write the cross product down. We dump all of the cross products that are parallel unit vectors, keeping the rest. So expanding this product here, we end up with all these terms right here. Now you'll notice that you've got all types of i's and j's and k's, so we're going to collect them in a way which will give us the components that we want. In other words, we're going to have all the components that are in the ith direction, the jth direction, and the kth direction. But this step here is just simply eliminating all of the self-cross products, so that's what this is. So if we collect the I, j, k's, this is what we get. We get this scalar times I, this scalar times j, this scalar times k. I want to point out that this is in the x direction. Notice here there's no x's. This is in the y direction. There's no y's. This is in the z direction. There's no z's. The other thing to notice is that we just flip these. So AYZ, AZ, BY. We just flip the order of that. That's a property of the cross product. This is a very common place to start with the cross product. We started from the geometric example where we determined the cross products of the unit vectors and we used the fact that it distributes. This is a workhorse definition, and we started with a geometric definition. Remember that this is what we ended up with for the geometric definition, where n hat is the unit vector normal to the product formed by A and B. Now if you go back to our brute force cross product here and change the y's and the z's to 2, 3, 2, 1, and so on, you can show that this quantity here is equal to a determinant. So A cross B is equal to the determinant of this array. This would be x hat, y hat, z hat, or I, j, k. This is the x, y, z components of A, x, y, z components of B. So that's what I've said over here. 1 equals x, 2 equals y, 3 equals z. So if you expand this determinant, you get exactly this equation up here. This is easier to remember, and so you might just want to memorize this because you can always expand it to get the brute force or workhorse definition. So that's basically what we're going to say about the cross product. The next time we're going to talk about the Kronecker delta, which we call delta ij, and we're going to talk about the Levi-Civita operator, which is epsilon ijk. These two operators are very useful for finding identities in the multiplication of vectors, so both the dot and the cross product, and later in the differential operators.